Welcome, advanced physics students. This screencast is covering Chapter 8, Forces in Nature, and it is in Unit 2, Mechanics in your textbook. 4 sections are in this chapter. This video is only going to cover Section 8.1, Newton's 3 laws of motion. And then within this chapter, there is Section 8.2 covering friction. Section 8.3, the 4 fundamental forces, and Section 8.4, gravity and gravitation. So first we'll discuss Newton's 3 laws of motion. So far we've analyzed how an object moves in terms of its velocity, acceleration, and displacement. And we really analyzed that in Chapter 7 when we were calculating how long it takes for an object to drop in free fall, how tall is the ledge from which the object was dropped, what was the range of the object when it was launched at a particular horizontal velocity. We examined all these things, but we didn't really look at why these objects move. And the why was not known until Isaac Newton published his Philosophiae Naturalis Principia Mathematica in 1686. Prior to this, Aristotelian thought suggested that objects moved according to their purpose or their nature. So the view towards objects was what's called teleological. And if we saw a rock roll across the ground, and if we saw the rock stop rolling, we would say, well, the rock stops rolling because that's what rocks do. And really this idea of friction stopping a rock from rolling forever and ever was not really well known. So in the Principia, Newton presented his 3 laws of motion that for the most part hold to today, and they have really great application whenever we look at the world of everyday objects, when we get into tiny objects the size of photons or things moving at the speed of light. The laws don't really work, but for everyday objects we handle, the laws work really awesomely. So Newton's first law is called the law of inertia. It stated that a body in motion tends to move in a straight line at a constant speed, and a body at rest tends to stay at rest unless acted on by an outside force. And since a force is considered to be a push or pull, it simply means a push or pull is necessary to change the present state of any body of matter. Now, think back at the times past when you would have gone to Kings Island or Cedar Point, and you're riding along horizontally, maybe at the top of a hill, and then all of a sudden, as the car that you're sitting in hits the drop, you feel your seat seemingly drop from beneath you. What you are experiencing is Newton's first law. Your body was heading towards a particular motion, and your body wanted to maintain that motion, and the sudden drop changed that motion. And the only thing that keeps you from being launched out of the train is the bar that is across your lap, or maybe a seatbelt, something like that. So that is how we would describe the action of the rider there. So the rider's body is maintaining the horizontal course it had prior to the drop, and the lap brace applies an opposing force, keeping him from flying out, fortunately. And then when we enter curves and bends, you probably can remember times when you felt a pull away from the inside of the curve. And you should know, spoiler alert, that this is not a centrifugal force that you are experiencing. Instead, your inertia, or your tendency to keep moving straight when the car turns, is responsible for that sensation. So friction is yet another force that acts on bodies in motion. Friction opposes motion directly and makes bodies stop. And if you can imagine frictionless or very low friction surfaces such as ice or air, objects slide nearly effortlessly. And since friction is prevalent everywhere, early philosophers believed that it was the tendency of objects to always return to a state of rest. They could not imagine objects being out in space or in a vacuum traveling in a straight line forever until they were hit by an asteroid or until they ran into a planet or hit a planet's atmosphere. So they just believed that it was the tendency of all objects to return to a state of rest. And the idea, and I just said this, the idea that an object could theoretically travel forever was completely foreign. So Newton's first law of motion then can be restated another way. In the absence of an external force, every body maintains its present velocity. And forces are always the consequence of an acceleration acting on a body, which brings us to Newton's second law. So in order to have any object change its motion, an object is going to change its motion when it either stops moving, moves faster, or changes direction. And we call all of these things an acceleration. And the only way that an acceleration occurs is if there is a force applied, and this is Newton's second law. The second law answers the question of how much force is needed to accelerate a body at a given rate. And this is what the equation looks like that we use. So note that force is directly proportional to the body's mass indicated by m, and the a, of course, is acceleration. Another way to look at this equation is like this. We would say that an object experiences a given acceleration, and the acceleration it experiences is directly proportional to the force applied and inversely proportional to the body's mass. So I just said that. So force has units of newtons, and it is defined as the push or pull, the force required to accelerate 1 kilogram of matter at a rate of 1 meter per second squared. And the unit of newtons then is defined in terms of 3 fundamental units. 1 newton equals 1 kilogram is the amount of force needed to move a 1 kilogram mass at an acceleration of 1 meter per second squared. So mass, length, and time are all units that are contained within a newton. Let's look at example problem 8.1 from your textbook. A force of 5 newtons is applied to a mass on a frictionless surface. What is the acceleration if the mass is 2 kilograms, or 5 kilograms, or 20 kilograms? So we would take the equation F equals ma, and we would rearrange it to solve for a to obtain a equals F over m. So for the first situation of a 2 kilogram mass, the acceleration that it would undergo if it was given a 5 newton push is 2.5 meters per second squared. Okay, so here's F over m. And in this case here, I'm just breaking out that newton into the units that make it up. If we solve for b, again we are doing a equals F over m. We have a 5 newton force, and it's divided by a 5 kilogram mass, and it equals 1 meter per second squared. That is the acceleration that body would undergo. And for c, the acceleration that it would go with a 20 kilogram mass is 0.25 meters per second squared. So we see a trend that for a given force, if that is held constant, of 5 newtons, if we apply this force against 3 different masses of increasing weights, we see that the acceleration felt by that mass decreases. So now let's look at using some of these proportionalities in the second law. So F equals Ka is equation 1 from your textbook, and it states that the force applied to a given body is proportional to the body's acceleration. So by this, if the same mass is accelerated at a given value, at a given acceleration value, by a certain amount of force on one occasion, and if that same mass is then accelerated at a given acceleration by a different force on another, we can put together this proportionality. F1 over A1 equals F2 over A2, with mass being held constant. So how would we use this in solving a problem? Well, if a force of 2 newtons accelerates a mass at a rate of 1.74 meters per second squared, how rapidly will the same mass be accelerated by a greater force, a force of 4.4 newtons? We are assuming for this particular problem that there is no friction. So if we use that proportionality that we saw on the previous slide, and if we solve for A2, we rearrange this equation here, and we see that the acceleration in the second case would be 3.8 meters per second squared. I hope this makes sense. You're taking a given mass. In the first scenario, you're giving it a 2 Newton push, and it accelerates by 1.74 meters per second squared. That same mass, we are more than doubling the force on it, and we see that the requisite acceleration is greater. It's more than double. So let's look at a different application. So F equals K prime times M, and this is equation 2 from the text, and it states that for a given acceleration, the required force to move a body is proportional to the mass of the body. And by this, if acceleration is held constant, we can derive this equation here. There's yet a third proportionality that we can derive. Since the product MA must be constant for a given value of force, after all, F equals MA, then it follows that M1 times A1 equals M2 times A2. So let's look at this particular, proportionality in example problem 8.3. An identical force is applied to 2 objects of different mass. One object has a mass of 2 kilograms and undergoes a uniform acceleration of 6 meters per second squared. The second object has a mass of 4 kilograms. What is its acceleration? So again, we're going to solve for A2, and we would take that equation from the previous slide, rearrange it to solve for A2, and we get the answer of 3 meters per second squared. So let's look at this idea of mass versus weight. Mass is defined by the amount of matter in an object and is the same no matter where the object is. However, weight is the force exerted on an object's mass by a gravitational field. So it doesn't matter where you are in the solar system or universe, as long as you're not traveling at half the speed of light or greater, your mass is going to be exactly the same. But your weight is going to change based upon whether you're on the moon, Mars, Earth, Jupiter, or heaven forbid the sun. So weight changes. So an object's mass remains constant, whereas its weight does not. For objects on Earth, we're going to do a lot of calculations for objects on Earth because this is a point of reference that's important to all of us. We can calculate their weight in newtons using F equals mg, and this is a special case of F equals ma, where g is 9.8 meters per second squared, the acceleration due to gravity. So let's examine example problem number 4. A car has a weight of 7 times 10 to the third newtons. Can you calculate its mass? Well, of course you can. And neglecting friction, what force is needed to give it a horizontal acceleration of 5.20 meters per second squared? Well, in the first case, we're going to use this equation, this form of F equals ma, and we're going to solve for mass, giving us this. We're going to rearrange this equation. So we solve for mass, and m equals F sub w over g, and we know that the car actually has a mass of 714 kilograms. Now, can we calculate its acceleration, or can we calculate, the force needed to give it a horizontal acceleration of 5.2 meters per second squared? Well, sure we can. Since the mass is 714 kilograms and the acceleration is 5.2 meters per second squared, we can solve it using F equals mg, and it equals 3,710 newtons. Now we'll look at Newton's third law. The third law states that for every action force, there is an equal but opposite reaction force. If your right hand slaps your left, it is applying a force that is met by an equal yet opposite force from the left hand. So there are three important rules that may be derived from Newton's third law, and the first one is that forces always occur in action and reaction pairs. Single forces are not possible. Okay? And the second rule is that action and reaction force pairs are always opposite in direction, equal along the same line of the applied force. We see the evidence of this. We have two spring scales. This one is fixed on a rod, and this one is being pulled. And in this case, this is the action force. I can't really read that. It looks like it's about 1,400. Well, it's showing grams. Is that right? But they should have put a force, a spring scale measuring force on here. So that's about 1,400. That's about 15,000 newtons of force being applied here. And this reaction here is showing exactly the same amount of force as a reaction force. Here's the third rule. Motion is caused on any object by unbalanced forces acting on the object. So in the case of a golf ball, the force of the club hitting the ball is met with the ball pushing back against the club. So we're looking at what's happening with this ball here. So we have the force of the golf club hitting the ball, and the ball's pushing back with an equal force against the golf club. And the ball, in turn, is pushing on the air molecules in its path, and the air molecules are applying an equal force on the ball. But if we look at all the forces acting on the ball, they're unbalanced. And that's why the ball is actually traveling. The unbalanced force comes into play because the club's force on the ball is much greater than the air's force on it. In this, we see unbalanced forces acting on the same object, and that's what's making the object move. So look in the second image down here. Note how the golf ball undergoes a deformation along this side where it's being hit by the club, but not in its interaction with the air. So there's an imbalanced force. This ball is feeling a very significant force on this side from the club, not so significant on this side by the air. So unbalanced forces makes it accelerate. So we're going to relate the second and third laws now. The equation of F equals ma, characterizing the second law, would have one think that there is only one force ever acting on an object, but there really isn't. In reality, this force represents the net force of all the unbalanced forces, and it really should be stated as this, that the net forces acting on an object is equal to the object's mass times its acceleration. So yeah, and where this here represents the net force acting on the object. So in the case of the golf ball, to beat a dead horse, there is a force acting on it from the club that is much greater than the force enacted on it by air. So let's look at another example problem from your textbook. Suppose two men are pushing a 25 kilogram box to the left. One is applying 16 newtons of force, and the other is applying 5 newtons of force, both to the left. What is the box's acceleration? Well, we know the net force acting on the box is the sum of the forces that are being applied left, which is 16 newtons from one man and 5 newtons from another, giving us 21 newtons. Now, this is a horizontal force, net force acting on the box. Because the box is not in free fall or it's not jumping up off the surface, we know that the normal force of the box is the same as the force due to weight. So those two forces cancel each other out. They're equal in magnitude, opposite in direction. So to figure out the acceleration, well, F equals ma, we rearrange to solve for A equals F over m, and A equals 16 newtons plus 5 newtons divided by 25 kilograms. We know that the box is accelerating 0.84 meters per second squared to the left. So other applications of the third law? Well, movement of a jet or rocket is the forward reaction to the backward expulsion of exhaust gases. The recoil of a gun is the backward reaction of the forward reaction of the bullet being fired. The sting felt by your hand whenever you're catching a fast baseball. The ball is exerting a force on your hand, but your hand is also exerting a force on the ball. And the push-up of your foot against the ground when you're riding a skateboard. These are all examples of action and reaction force pairs. So here's a final illustration. Imagine if you have a block, a wooden block, that is attached to a spring. And let's say that it is mounted here. If you pull on this spring, you can actually feel the spring pulling back on you with an equal force, but it's acting in an opposite direction. And if you actually try to compress the spring, similarly, you apply a force to compress it, but the spring is pushing back against you with an equal force. And we learned about Hooke's law a couple chapters back. So that's all I have for this section. If you have any questions, feel free to drop me an email. I will see you guys in class.